This is Syzygy, Episode 1, Planets. Lots of planets. Welcome to Syzygy, an astronomical podcast, a universal podcast, a cosmic podcast. We're going to need a good tagline for this. This episode is all about planets, and in particular, a discovery in February 2018 of planets in a galaxy far, far away. I'm Chris Stewart. I'm not an astronomer. I used to be a theoretical physicist, and then I realised I actually much prefer talking to people about science than actually doing it myself. And joining me at the microphone is Dr. Emily Brunsden, who is an astronomer. Hi, Emily.
Hello.
So, Emily, before we get into the whole planets in the news thing, we'll get to that in a minute. By way of introduction, this is episode 1, so why don't you tell us a little bit about yourself? You're an astronomer, so what kind of astronomer are you?
Yes, I'm an astronomer. I work mostly in stellar astrophysics, so that means that I study stars as part of my bread and butter. I'm an observer, so I work on lots of telescopes around the world, spending my nights staying awake and looking at the lovely data that comes in from these beautiful telescopes. I come from New Zealand, which is where I did my undergraduate study, my PhD, and I work now in a field called astroseismology, which is not only a fun word to say, but is actually all about the physics of stars, trying to work out what's going on inside them based on what we see from the outside.
Seismology, I mean, when we talk about that on Earth, we're talking, earthquakes and movement of tectonic plates and things like that. What is astroseismology?
Basically the same thing, but we apply it to stars.
Starquakes.
Yeah, so hopefully we'll get to do our own special podcast on what gets me up in the morning and to do research.
We're going to have to do that. That just sounds so awesome. Okay, well, in this particular episode, though, we're going to talk about planets because back in February 2018, 1 month ago as we're recording this, there was some pretty interesting news about planets not in our local area, not in our galaxy, in a completely different galaxy. But in order to get there, we should probably back up a little bit and just talk about planets in astronomy. So why don't we back right up and talk about when we first started realizing that there were planets at all. We figure we're on Earth, we're on a planet, that's one. But when we look up at the sky, there's lots of tiny little pinpricks of light. How did we know that some of those were planets?
Well, it took us quite a long time to get a description of what a planet is. Actually, the word is really interesting itself because it comes from the ancient Greek. It means a wandering star. And that pretty much describes how the planets in our solar system appear to us as we observe them from Earth. If you go and look at the night sky over the course of many, many nights, you see that some stars tend to move in a different way against the background of all the other stars which are moving with the Earth's rotation. And so these special wandering stars who are just sort of going on their own paths were identified as their own special type of object, these planets.
Now, these things they're not whizzing across the sky. So what you're talking about is if you spend enough nights looking up at the stars, you notice slowly but surely that some of those pinpricks of light are moving against a backdrop of other stars that seem to be pretty much fixed in place. But some of them aren't.
Yeah.
And those are what we call wandering stars, planets.
Wandering stars, planets, yes. And so we started off with some of these planets are the brightest things that we see in the sky. So we have Venus, we have Jupiter, incredibly bright things. So they weren't really difficult to observe before we had telescopes. And we were from this able to construct a model of what our solar system might look like. And those very first models, because we didn't feel the Earth was moving, we don't feel it as it goes around the sun. So we just assumed it wasn't. And we thought that everything else revolved around us here on Earth.
Observationally, that makes a lot of sense. I mean, the stars move across the sky, the sun, the moon, the planets all move across the sky around us. That's what we see. It kind of makes sense. But it's not as simple as that, is it?
No. And actually, once we started to make a model of how this might work and do some maths to work out, try to predict where the planets should be in the night sky, we found that there were some problems. Basically, these wandering stars or planets weren't doing what they should do in the sky.
They weren't going around in really simple orbits. It was complicated.
It was complicated. And sometimes they even went backwards in the sky, which was a little bit annoying.
So these models started to get more complicated then, that rather than having a circular orbit around the Earth, circles upon circles were introduced.
Yeah, these are called epicycles. And they're sort of interesting. So if you imagine a planet going around the Earth, then you imagine it going on a small mini circle as it's going around on this bigger circle, which is its orbit. So and that's an epicycle.
At some times as it's going around a planet, because of these epicycles might go backwards in the sky and then forwards again. So that was a reasonably good predictor for what we actually saw in the night sky.
It was, and actually gave reasonably good predictions until we started making more and more precise measurements, particularly started in the 15th, 16th century. And they started to not work again, these models.
So at some point, simplicity won, in the sense that rather than these very complicated circles upon circles upon circles to explain strange movements of planets in the sky, if you just then say, well, maybe we're all just going around the sun, that suddenly became a much better model for what we're seeing.
Yeah, initially it didn't work as well, actually, as this circles upon circles, but that's because we thought that everything should be circles. And it took us a while until Kepler really came along and to break down what circles, that planets shouldn't move on circles. And they should actually move on ellipses, which are slightly elongated circles. And now we're starting to talk about a model which works in our solar system.
And so from that point, with a heliocentric model, the sun at the center of everything started to become much simpler. You got planets going around the sun in not circular but elliptical orbits, and the solar system became much simpler.
Yeah, so we had, originally 9, now 8 planets in our solar system.
Poor old Pluto. We're not going to go there. We might, maybe some other time. We'll just leave poor Pluto out of it.
And that was basically the status quo for a very, very long time. It took us a long, long time to figure out that, or to observe other planets around other stars.
So that's the next big jump out, isn't it? Once we've lost our central position in the middle of the universe, everything goes around us. Not true anymore. Go around the sun. Planets orbiting stars. Can we be the only star that has planets around it? So when did we first find planets around other stars?
Well, we had a few hints of these using techniques in the 80s, but it wasn't really until 1995 that we got the first confirmation of finding a planet outside of our own solar system going around a different star.
How do you do that? How do you find a planet around I mean, you look up the night sky, stars are literally pinpricks of light. They are tiny. How do you spot something even tinier and dark? Planets don't give off their own light. How do you spot that?
So it is incredibly difficult, and we as astronomers basically have become used to using light to its absolute maximum capacity. It's almost all we get from the universe. So what we do is we look at the light from the stars that are hosting these planets, and we see if there's any changes that might indicate that there's a planet going around this star.
Planets are small, so the changes you're looking for must be really small.
Incredibly tiny, a few fractions of a percent.
As you say, astronomers are getting very, very good at using the light that's available to them. So what kind of changes then? What does a planet do to the light coming from a star that shows that it's there?
So we've got a few different ways. One of the most successful ways we have is called the transit method. And this is where you have a host star and basically the planet moves in between us and the host star. And what it's done is it's blocked out a tiny, tiny bit of the light that we would normally see from the star. So over time, we get to see a periodic blocking of the light. So the star appears just a tiny little bit dimmer again and again and again as the planet goes around in its orbit.
It's got to be tiny, though. I mean, what kind of drop in intensity are we talking about?
Sometimes down to 1/millionth of a percent.
Good Lord. I mean, that's extraordinary.
Really, really tiny.
But, okay, hang on. How do you find that? There's no way in the world that you can, okay, we're going to look at that star there and wait for its intensity to drop by a fraction of percent. Nope, no planets around that one. Okay, we're going to look at this star over here. That's obviously not what's happening. So what's going on?
No. So, we didn't really know how many planets to expect in the galaxy when we first started this. So we thought, let's just look at an awful lot of stars and see if we can find planets around some of them. So back in the 2009, we sent up a telescope called the Kepler Space Telescope, and Kepler started to observe 150,000 stars all at the same time.
At once.
All at the same, in the same constellation. And we just started looking and seeing which one of those might have one of these transits.
So you've got this picture of what do you say, 150,000 stars at once in the field of view, and watching to see if any of those dip just slightly.
Yep,
in order to spot a
and
planet.
do that for 4 years and see what you get. And that was Kepler.
So Kepler was fairly successful, I think it's fair to say.
Very, very successful. It's definitely been our most successful planet hunter to date. So we've got nearly 3,000 planets now that have been discovered by Kepler.
So in the space of about 20 years, we've gone from a few, the first ones, to thousands.
Yep.
With thousands
nearly
more
4,000
possibilities.
total now, yeah.
So I'm guessing that the first ones that we found, they must have been pretty big.
Yeah, so you can imagine the easiest planet to find is one that's going to block the most light. And the planet that's going to block the most light is going to be, first of all, very large. And it's also going to be quite close to the host star so that it blocks the most. And indeed, these were the planets that we found first. We call them hot Jupiters because they're very close to their host stars, usually about or within the orbit of Mercury. And they're really big. And what's interesting, of course, is that we don't have such a planet in our own solar system.
Yeah, that's really different to what we've got. We've got small, really big, and then, getting a bit smaller as you go further out. But the big planets in our solar system are quite a long way out.
Yeah, and we think that that's basically where they formed. So you need to actually move a little bit away from a star in order to have a lot of gas, for example. So things that are very these big gas giants of Jupiter and Saturn, they can't form very, very close to their host stars. So we think that these hot Jupiters either got captured, so came into their systems from another place, or more likely they migrated somehow from basically where Jupiter is in our solar system, all the way in.
Wherever they came from, they were the first ones you found because they were the easiest to find.
Definitely, yeah.
But as Kepler got better and better at spotting planets, it must have found all sorts of things.
Yeah, so we got basically the whole spectrum of different types of planets, different masses. We found things that are now the size of the Earth, and all sorts of different orbits as well.
So out of thousands of exoplanets that we found, is our solar system normal? Is the Earth typical?
It seems so. We've actually got 2 systems that we've found now which have 8 planets in them.
Same as us.
And we expect basically on average in our galaxy to find a planet for basically every star that we see.
Every star in the galaxy. So hang on, there's what, 100 billion or so?
Yeah, maybe
stars
even 300 billion.
in the Milky Way. And on average, every star would have a planet or so.
And it was only with the wonderful results from Kepler, for example, that gave us the statistics to be able to say that, other than just being able to find the odd planet here and there.
It's been a hell of a century for human, we are the centers of the universe, we're pretty special, to every star in the night sky has probably got a planet around it. So
it's very exciting.
So that's exoplanets and Kepler. But just to be clear, Kepler finding all of these thousands and thousands of planets, those are all in our galaxy. Right?
Yeah, and very, very close to us in our galaxy. So really in a small little bubble around the Earth. If you imagine the galaxy is one of these beautiful grand spiral galaxies. You can see lots of really nice pictures of similar ones out there in the universe.
It's got spiral arms sort of swirling out of it.
Beautiful spiral arms. And
as Douglas Adams said, we're just sort of in this, I'm paraphrasing him here, but we're in sort of an uncharted backwater of one of these spiral arms.
Yeah, so we're about 2/3 the way out. It's not we're not even really in a spiral arm. We kind of got this little spur off to the side.
We're in a suburb. We're in a far-flung suburb of the galaxy.
Yeah, it's almost a really uninteresting little plot of our...
We're in a nondescript 60s brick cul-de-sac of the Milky Way galaxy. Okay, but Kepler's been looking at hundreds of thousands of stars just in our local area.
Just in our little bubble.
In our suburb.
Without even thinking about what there might be towards the edge of the galaxy, towards the center, or even out to the sides. We just can't. We don't have the techniques that are developed enough to be able to observe those kind of planets yet.
But from looking around at all of the stars in our local area, in our suburb of the galaxy, statistically, all of those stars would have planets. And so extrapolating across the galaxy, our area is probably not particularly different. And so we assume that every star in our galaxy, on average, probably has a planet or maybe more. So that's what we've found so far. Coming back to our news story then, in February this year, February 2018, there was a big announcement in planetary astronomy, in exoplanet astronomy, which is the first planets found outside our galaxy. So talk us through this one.
This completely floored me when I first read it. I just couldn't quite... The headlines were very, very tantalizing, and I couldn't quite see how we would go from just our local neighborhood to suddenly a whole nother galaxy. And what's even more amazing is this is not just our next door neighbor galaxy. This is not very close to us. This is a galaxy that's 3.8 billion light years away.
That's a long way.
It's a very, very long way.
Just to be clear, that's a very long way away.
So even the beautiful pictures that we see of these lovely spiral galaxies, they're from relatively close by ones. And this is something that is much, much, much further beyond that.
Okay, so we have a very far-flung, distant galaxy. What's it called? What's the name of the galaxy?
Well, I don't actually know if it does have a name.
It's that far-flung, and that's that, nondescript, unimportant otherwise. It doesn't even necessarily have a name. That just sounds impossible. How on earth can you possibly find planets in a galaxy like that? That's ridiculous.
It is. Well, it's amazing. And what we're looking at now is we're not looking at the light from individual stars. So we're not doing something like what Kepler did and looked at stars and waited to see.
Even in the hundreds of thousands, you can't even see the stars in that galaxy.
No, we can't.
So this is completely different then. So what are we doing?
Well, there has to be something bright then, because we know that if we're going to be looking at something this far away, there has to be something very, very bright. And actually the object that is very, very bright, that's providing all the light that we see, is something called a quasar. And that's not in the galaxy that has all these planets. That's behind the galaxy.
Even further away.
Even further away, at a massive 6 billion light years away.
So there's a syzygy, if you like. There's us, there's this galaxy in between, and then there's this far-flung, incredibly bright quasar.
Yeah. And the quasar does have a name.
At least the quasar has a name.
The
Something
quasar's
has a
called,
name in this
well, it's
story.
got a very, very romantic name called RxJ11311231.
You astronomers need to get your act together. This whole naming thing, we need to talk about that in a future episode.
Yeah. So a quasar, what a quasar is basically, it's a type of galaxy that's incredibly bright. And we wouldn't be able to see it unless it was, because it's just so far away.
Why is it incredibly bright? What's going on in a quasar?
Well, this is very exciting. In quasars, you have a black hole in the middle of the galaxy. Actually, that's fairly standard. We think most galaxies probably have a supermassive black hole in the center. But these quasars have black holes that are doing something really special, and that they're feeding. It's really nice how we personify
really
these black
sinister,
holes.
Doesn't it?
These feeding black holes. And so what's happening is material from the center of the galaxy is falling into the black hole, and some of that energy gets shot out along the top of the black hole into these huge bright beams, basically, of light. And it's that beam that we're able to see from this quasar.
All right. So incredibly far-flung quasar, galaxy in between. So how does that allow us? I'm struggling with the whole, and now we've got planets thing. What's happening?
So what is happening is the light from that quasar is being lensed by the light that's from the galaxy. And so it's operating a little bit like a telescope lens or a binocular lens, and it's actually focusing the light of that quasar such that it makes it appear a little bit even brighter to us.
Now, this is an Einstein thing, isn't it? Einstein, when he came out with his general theory of relativity, he said that gravity is a result of the bending of the warping of space-time by massive things, energetic things. And one of the central points about relativity is that there's not really any difference between energy and mass. If something has mass or if something has energy, either way, gravity can affect it and it can affect other things. In other words, light, which has energy, can be bent around really massive things like stars or galaxies.
Yeah, and we even observed this to prove Einstein's theory of general relativity with the sun. So we waited until we saw a total solar eclipse. So the moon went in front of the sun, blocked out all the light, and we could see the background stars behind the sun. And it turns out that they were in very slightly different positions than they are when we measure basically when there's no eclipse, when there's no sun in the way, basically bending the light. So we know that even the sun has enough gravity to bend light. A whole galaxy full of stars is going to have an awful lot of lensing capacity.
So the distant quasar, the light from that is being lensed by the galaxy in the way. And so you can see, a brighter image of that quasar?
And we see multiple images of the same quasar. So it's a little bit like a funhouse mirror where you get all sorts of weird distortions of the light.
So it's not acting like a simple lens, it's acting like a crazy lens, and it's giving multiple pictures of this distant object.
And there's 4 main images that we can actually see of this quasar. And we can study those images and we can learn something about the gravity that this intervening object, this galaxy, is having the effect on the background light from the quasar.
So you're working your way backwards from this is the images that we can see of the quasar. So we know how lensing works, we know how gravity works, so we can work backwards to figure out what is this thing that's in the way, the galaxy, what's the distribution of mass in that? What's it made of? That's what's happening here.
Exactly, yeah. And the title of the paper that came out by Zinyu Dai and Eduardo Guerres was Probing Extragalactic Planets, Therefore Using Quasar Microlensing. So there's a lot of big words in there and quite technical words, but actually you can start to see where this is coming from. So we're using this quasar, the fact that it's microlensed, to find out that there's some extra galactic planets in this host galaxy.
Okay, but I mean, it just sounds ridiculous. How do you get from, I can understand, sure, that the light from the quasar can get lensed in some crazy way by the gravity, by the mass and the mass distribution of that galaxy. I can see that, I can understand that, sure. How do you get planets from that? I can understand that you might well be able to say, okay, well, we think we see a galaxy of such and such a mass in the way. That would make sense. Maybe it's kind of this shape. How do you get planets?
Yeah, well, it's that mass distribution that you mentioned that's really important. So it matters how much mass you have of different sizes. So we know that galaxies are primarily made up of stars, lots of stars. So we make a model, basically, of what this galaxy is going to be like in terms of its mass. We're going to add in the mass of all the stars. You might have a few 100 billion stars. Now, there's stars of different masses. We have very, very big stars. We have very, very small stars. We know roughly what this distribution should be. We know there's not many very, very large stars. We know there's an awful lot of very, very small stars. And so we put that into the model, first of all. And then we say, okay, what else is there in the galaxy that we're going to use to create this model? Well, we know there's lots of gas and lots of dust. So we put those bits into the model as well. Turns out that they don't have a huge effect in terms of mass. And then basically to be able to make a model that accurately represents the lens, we need to add in something else. And what we had to add in, or what was found in these models to be added in, was that there had to be planets added in order to create the lens of the quasar that we see in the sky.
So you built up a model based on what you know about galaxies, what they're made from, and you're adding bits and taking bits away in order to explain what you see in this lensing observation. And planets have to be in there. But correct me if I'm wrong, these are not the kind of planets that people would normally think about. These are not planets going around stars.
No, so we call a planet that's going around a star a gravitationally bound planet. It's in a system. It's most of its gravitational effects are to do with the interplay between the gravity of the star and the planet. So these planets that were found, had to be put into these models. They were kind of ordinary in the sense of they're like the planets that we have in our own galaxy. They have masses of something the size of the moon up to something the size of Jupiter, so kind of stuff that we're fairly familiar with. But what's really exciting is those planets are not going around the stars.
So where are they? They're just floating around.
Yeah, and these are what we call rogue planets or free floating planets.
I like rogue. Let's go with
planets, that. Yeah, and so they're not going around a star anymore. They've somehow been kicked out of a planetary system and are now just traveling through interstellar space all on their lonesome.
So how many are we talking about? How many of these rogue planets have been spotted in this way?
Well, in our galaxy, we've only got a few, maybe 50, 60, something like that.
But in this study, in the lensing study, how many did they find?
Well, that's the exciting thing. They had to put in 2,000 per star.
2,000 per star.
2,000 planets ranging from the moon to Jupiter per star in
a
the
galaxy of hundreds
of billions of stars.
Holy cow!
That's utterly staggering. So, talk about overachieving. You're not only finding.
Hey, Kepler, hold my beer. Hang on a second. We got. I mean, that's trillions of planets. So, all right. I mean, we've been talking a little bit so far about we here on Earth. We're not so special anymore. We're not the center of the universe. We're not even in a particularly interesting part of the Milky Way. Let's face it. Is this discovery of all of these rogue planets in this far-flung galaxy that's not even special enough to have a good name, do we think that the same thing would be true of the number of rogue planets in our galaxy?
Well, we just don't know. I mean, this is a new discovery, and we've got to think about and try and understand how similar this host galaxy might be to our own. We know we've got some rogue planets in our galaxy, and actually they were found using pretty much the same technique, the same physics, because they're not going around a star, so they can't have any effect on a star that we can see. They don't put out their own light, so all they've really got that we can try and observe is their gravity. So in the case of finding planets these rogue planets in our own galaxy, we are looking for this nice syzygy where you have the background star and you will have the free-floating rogue planet come in between us and that background star, and it will again lens the light from that star, focus it, make it appear a little bit brighter than it should do, and then it will sort of carry on its merry way.
But that's got to be a staggeringly rare and minute event, because when we were talking before about spotting exoplanets and the transit method, at least a planet's going around the star. If you miss it one time, you've got a chance of seeing it the next time it comes around. This is a rogue planet that just happens to wander in front of any random star that you might happen to be looking at. That's astronomically unlikely.
Yeah, but we're used to dealing with things that are really unlikely in astronomy, and we're really good at dealing with this problem by basically observing an awful lot of things. So if an event is really, really rare, you observe a lot of objects where you might expect that event to occur. Unfortunately, we've got quite a lot of stars in our galaxy that we can observe, and so we observe hundreds of thousands, if not millions of stars, and we just wait for these events to happen.
As it turns out, I mean, if the stats from this galaxy that's been observed in the paper you're describing, with the thousands of rogue planets per star, if that turns out to be the same in our galaxy, then maybe it's not as rare as we might think. These things might be microlensing stars all the time.
Well, we have been observing our own galaxy using this technique for quite a long time now. And as I say, we've only found maybe 60 odd of these microlensing rogue planets on our own. So it's difficult to say whether we have a different population of these rogue planets in our galaxy or if they're the same and we're just not good at finding them. And that's going to be definitely something that we're going to be researching further.
So this paper that made the news, February 2018, this is the first group of planets, population of planets, I guess you'd call it, found outside of the Milky Way galaxy, yeah?
Definitely, but it's not the first individual planet. So we have found at least 3 others that we think are probably planets from other galaxies.
Okay.
Now, one of them, which is very exciting, also has a really exciting name called HIP 13044b.
We've talked about this name.
We're going to have to start thinking about these names. This is actually a planet that's inside our galaxy, but we believe that was actually born in a different galaxy to our
Hang
own.
on, sorry. It's in the Milky Way, but you reckon it's not from the Milky Way. So, okay, I'll bite. How did it get here?
So as part of the host star that has this planet, basically is part of a group of stars called the Helmi Stream. And this Helmi Stream is the core of an old galaxy that's being ripped apart by the Milky Way as the Milky Way galaxy basically consumes this other galaxy.
This is a thing. It's got a great name, hasn't it? This is galactic cannibalism.
Yep, and that's an official astronomical word.
So galaxies collide, and I guess if you've got a big galaxy, it basically just eats the smaller galaxy.
Yeah, exactly. And we can trace back basically the origins of this Helmi Stream to being, it used to be a galaxy. And maybe about 6 billion years ago, this planet was born and came into our galaxy at a later date.
All right, so that's one from another galaxy. You said there were others.
Yeah, so we have found potentially something which is about 6 times the mass of Jupiter in our nearest neighbour galaxy.
Andromeda.
Yep, that's only 2.5 million light years away.
Yeah, that's just
Only.
over there, just next door.
So we found that in about 2009. So that's, again, a candidate planet, so it hasn't quite been confirmed yet. But we even found another planet from a quasar before. And this was one that's 4 billion light years away. And we found a planet that's maybe about the mass of the Earth. So an individual planet from a quasar microlens.
A planet. Is this a rogue planet microlensing a quasar?
That's right, yeah.
You astronomers, you're amazing. You know that?
It's so exciting. It's so exciting because you can never quite predict what's exactly going to happen next. Never would I have thought as an astronomer even that the next planets to be found would be in such a distant galaxy. And so many of them.
If I was an astronomer, I'd just wake up every morning with a big grin on my face. You know, what's going to happen today?
It always has the potential to surprise you. So basically today, as we talked about, we found thousands of planets per star in a distant galaxy that's so faint we can't see. That's basically, we can see it because we're looking at a black hole that's behind it. It doesn't get any better than that.
You've been listening to the Syzygy podcast. If you've enjoyed the show and you want to check out any more information about the things we've been talking about, the astronomy that we've been talking about, check out the show notes. There's all sorts of things in there. Links to news articles, links to the original papers when we can find them.
And you can follow us on Twitter, SYZYGY Pod, or just check out Syzygy FM, our website, and get in touch. Tell us what you think.
Syzygy is produced by me, Chris Stewart, and co-hosted by Dr. Emily Brunsden from the University of York's Department of Physics, nestled down there on the shore of Europe's largest plastic-bottomed lake. If you've enjoyed the show, tell your friends. Find that science nerd in your extended family and send them our way. And if you like, give us a boost with a review on your podcast directory of choice. We'd love that. Otherwise, we'll be back in a week or so for episode 2.
See you later.
Bye.
I don't know if you sign off pods like that.
We'll give it a go. Joining me at the microphone is Dr. Emily, who is an astronomer. Hi, Emily.
Hi.
So I'm going to start that again because I
That was
completely
a really weird hi.
didn't do what I was going to do.
Fine, that's fine. It was a really weird, like, hello.
Hi. Check out the show notes. There's all sorts of links in there to we're going to start that again. That was shocking.